Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Lab of Linear Control Systems. This is the lab manual that we are going to follow for this lab, and I'm sharing this with you via Google Drive link. Let's look at the list of experiments that are supposed to be done in this course of linear control systems. The first one is the introduction to the hardware and the software that we will use in the lab. DC motor controller, motor control trainer kit. So DCMCT. It is sponsored by the company Quanser. Quanser has made this. So after the introduction, we move on to the experiments of modeling the DC motor. There are two labs for the same thing. And in these two labs we complete the practical work of modeling the DC motor in the software of Quanser, that is QICII, the interactive interface, Quanser interactive interface software. Okay, after that in this list we have the modeling of various control systems in MATLAB. And in fifth lab, we model these systems in Simulink. Once the part of modeling is done, then we move on to the speed control and position control experiments. So speed control 1 and speed control 2 both are done on the hardware kit. Then position control, robust control experiment is done both in MATLAB and on the kit, while position control 2 lab works are done on the hardware board. After that we move on to the MATLAB part of the lab, and in this we explore the curve fitting toolbox, the single input single output tool controller design, state feedback control and output feedback control labs are done later when you have covered these topics in theory. For now, these 2 weeks that we are going to do in distant learning mode till 28th of March, I'm starting off with the MATLAB the labs that are be done in MATLAB, lab number 4 and lab number 5, that is modeling the various control systems in MATLAB script file and modeling the systems in Simulink. Lab number 4, linear system analysis in MATLAB. We are going to analyze a few linear systems in MATLAB. The theory background is from chapter number 1 and chapter number 2 of your course book. All you need is a MATLAB installed computer. We are going to see various system definitions. How can we define a system in MATLAB? One of the methods is to use the command TF, that is transfer function. You make a variable and you equate it to TF using the command TF and pass on the numerator and denominator values. What it does is it creates a continuous time transfer function with the numerator and denominator as specified by you, and the output is a transfer function model object where the numerators and denominators are arrays. So if you type something like this, 101 the numerator coefficients and 121 the denominator coefficients, you will see the output as s square plus 1 because there is no term with s, and s square plus 2s plus 1. So this is the continuous time transfer function, that is the output of this particular command. So this is how we have defined our system. This was one method to define the system in MATLAB. The other method is to use a rational expression for a single input, single output transfer function model. What we can do is we can first define S as the transfer function variable. So we define TF inverted commas S, and we can then simply write the equation in running form just like you type something in the Microsoft Word document. So now whenever you are using this thing S, it means you are referring to the variable S square to S here, right? Otherwise if you write, it gives you an error. So we first define it that we are going to use this S as the transfer function parameter. So it also we are exploring the same different ways to produce the same thing. So it also produces the same transfer function. Another method is that you are already familiar with zero pole and gain, ZPK. So you pass on the arguments in the same order. First you give the zeros, the poles, and then the gain value. It creates a continuous time zero pole gain model with zeros, poles and gain, and the output is again a model object which stores the model data. So the gain is a scalar value while these are the arrays. And in Simulink we can do the same thing by using the LTI system block. And this LTI system block we have is present in the control system toolbox, and when you double click that particular block, then you have to follow any of the 4 methods that have been mentioned here in these bullets. So your task is to use all of the mentioned commands to define a 5th order system. Students, every one of you have to define their own 5th order system, because we are going to perform various tasks on that particular system. So this is not a group activity, it's an individual task. So each individual has to define his or her own 5th order system with all these methods mentioned here. We can use the model interconnection. By model interconnection, I mean that we can interconnect various components to make a complete system. Say for example, you have been given a block diagram, and then you divide that block diagram into the various components and then interconnect those components. For example, we have this block diagram which is one input R and a final output Y. The input R passes from a filter f of s, and it gets added with the branch, that is the output being fed to a single model, and this C here represents the controller and this G represents a plant overall. So it means that all these square blocks, all these blocks can transfer functions in themselves, right? It could be 1 by s plus 1, it could be 1 by s plus 1 into s minus 2. So we are going to interconnect all of them. So how can we connect the models? This table will be very helpful in this regard. If you see that 2 blocks are connected in series, just like C and G here, you can either use the command series and pass on the 2 functions h1 and h2 separated by a comma, or if you want to write them in arithmetic expression, you can simply take product of the two. If you see the 2 systems are written in parallel form, like one input is fed to h1 and h2 and the resultant is the summation of the 2 outputs, so you can use the command parallel, or you can add the 2 systems simply. What if the 2 outputs are being subtracted from one another? Then the only difference will be the minus sign here, and the arithmetic expression would change to h1 minus h2. If you have a feedback system, just like in the above example, the output was fed back after passing through s of s. So if there is a feedback system like this, where we are taking the difference of the feedback output and the input, you can use the command feedback and pass on these 2 systems. These 2, I repeat again, these h1 and h2 are separate transfer functions. Or you can write it like this. The mathematical expression for this would be h1 over 1 plus h2 into h1. You must have done something similar to this in the courses of electronics, but this is not recommended while using MATLAB. We'd recommend you to use the command feedback. And if there is a system, value of the transfer function is used as an inverse, like we were using h2, but now we are going to use h2 inverse, which means we are going to divide h1 by h2. So there is no such command available. Rather, we have to write it in the arithmetic expression. Okay, after defining the systems, we can use the connect command to connect all. After all of this, we can use the connect command to connect all the components together. For example, we have some system B1, and the error of B1 is output error of B1 is input to the B2. So we are basically connecting B1 with B2. So I can use the command connect and pass on the argument B1 separated by a comma with B2. So if we want to take inverse of some system, we can use inverse command. And so in this example, you have been giving the values of all these components separately, and then we have to connect them to make a complete system, right? So keeping in mind that you have been given G in the form of zero pole gain. It could be anything, but in this example, they prefer to write it in the form of zero pole gain. So this is a transfer function with no zeros, 2 poles and 1 as the gain. Then there is a controller, and the type of the controller is PID, which we will learn later in the course. For now, you can simply write this command and it will define a controller. with these values. After that, the component S that was in the feedback loop, it is given as the command transfer function, and zeros and poles are given, and similarly the filter is given with the command TF. So the plant G, it is a zero pole gain model with a double pole at S is equals to -1. It has two poles at -1. So now just think of the block diagram and start connecting them. First, the controller and the plant models are being multiplied with one another. So you can write H is equals to G product C, and you know that we can also write the product as H is equals to series of C and G. And then the feedback equation can be used. You can after having this value H, now we will replace these two blocks with H, right? Now H and S are in feedback to one another. So if they are in feedback to one another, we can write them in this form, H1 by 1 plus H2 into H1, which makes it look like H over 1 plus H into S. So we have already defined all of these functions. Now this system is being developed step by step. Please read the note here. You do not have to use the model arithmetic as it was already written that it is not recommended, because it will computationally duplicate some of the values of the poles, which might lead to the inaccuracy in the system. You can use the feedback command here, and after that we have to construct the entire closed loop system, which is simply the product of the two results, because once you have solved this feedback, it will result into one system, right? All of this is being solved, so there will be one block, which means that now f of s and that block are in series with one another. So the final output would be the product of the two. This is example number 2, and it is now a bit complicated. You might need to solve some of the intermediate stages to simplify it. Here, this is the initial input YSP and the final output Y. So we have to make a transfer function Y over YSP. This example actually illustrates the use of the connect command. The code is given to you. We are defining these P, C, GP, DP and F. This is given to you, what is the transfer function, and once you define all of them, the junctions where there is arithmetic addition or subtraction can be done by using the command sum block, SUMBLK, and you define what do you want this sum block command to do. You have already defined the inputs and output YSP and Y here by using the dot operator. For block P, just let's elaborate this. For block P, the input is U and output is Y. So you write P dot input name is equals to U in inverted commas, P dot output name is equals to Y in inverted commas, right? After that, you are explaining the other blocks, and once you are done with this, you just use the command connect and pass on all the arguments to it, all the main blocks and the two main input and output, not the intermediate inputs and outputs, and the junctions of summations, sum 1, sum 2 and sum 3. So this is example number 2. You have to use the same code and see the results in MATLAB. After this, this is your second task. We are done with the examples. One task of making your own fifth order system. This is task number 2. You have to define the following in MATLAB. Number 1, the example 1. Example number 2 mentioned in this manual. The DC motor position and the DC motor model is given to you here. How can you define the DC motor position? They have given you the DC motor transfer function as K by S into JS plus B into L into S plus R plus K square. And where are the values of all these K, L, J coming from? They are given here, right? You just have to implement this in MATLAB. You have to define them in MATLAB. This bullet number 4 is excluded for now. Once we have defined these systems, now we are going to analyze them by using various commands. We can find the impulse response of the system by using impulse command and giving the system whose impulse is to be found in the input argument of impulse. So if the model is, for the command would be same, but the result that you see for multiple input systems would be a collection of the impulse responses for each input channel. And if you use system comma t final, it simulates the impulse response from t is equals to 0 to the value of the t final that you give. After that, you can analyze the step response of the system. What if we give a step input to this system? So you are going to use the command step, and you can also find out the step info by passing on these values to step info. So the step info returns you the rise time, the settling time, overshoot, undershoot, peak and peak time, various values, right? After that, we are going to see the stability analysis of the systems that we have defined in previous task. We can see the poles by using the command pole, zeros, damping of the system by using the command damp, and pole zero plot. So these are various commands that you just have to give input, and the input would come from the previous task. Task number 2. The two examples and the DC motor model, you have to perform the stability analysis by seeing the number of poles, zeros, the natural frequencies by using the damp command, the pole zero plot command, the pole zero map, and all of these 7. You just have to explore them. What is the significance of these commands? What do they do?